Alright, let's get to some real applications of Laplace transforms, beginning by discussing some more Laplace transform formulas. So here's one. What is that? This is called the Heaviside step function at the point A. So it's defined as follows. You take a number A, like 3 for example, and you define a function. It does something really simple. It's just 0 for all of time, but then it jumps up to 1 after t is greater than or equal to a. So if you want to compute the Laplace transform of this function, you are integrating it from 0 to infinity against e to the minus st as usual. But then you break the integral into two parts, one for t from 0 to a, and the other integral for t from a to infinity. Now, when t is between 0 and a, your function is 0. So this whole thing's gone. When t is greater than a, however, you have a 1 here. So what do you end up with? That. Hence the formula, the Laplace transform of the Heaviside step function at a is equal to this expression. Now, this is a useful function. Let's talk about another one. Suppose you have a function f, and let's suppose we already know what its Laplace transform is. Suppose we define this shifted function, tau a of f of t. It's this function that it's a translation of f times a Heaviside function. Let's compute the Laplace transform of the tau shifted function f. So the Laplace transform is found by integrating the function against e to the minus st dt. Now we break apart the definition into two parts. There's going to be an integral from a to infinity, and then from 0 to a, this function is 0 because of the Heaviside function being 0 as t goes from 0 to a. So this integral is really just from a to infinity of this function. But then, if we substitute u equals t minus a so that du equals dt, you end up with this, which you can rewrite as this using rules of exponents, bearing in mind that e to the minus as is a constant as far as u is concerned, as far as this integral is concerned, so it can be taken out of the integral. So we're left with the integral from 0 to infinity, f of u, e to the minus su du, times this little thing here. But what's this whole integral? It's nothing else but the Laplace transform of f. So what we actually have is that the Laplace transform of the tau shifted function is this. And I've written that formula here. Next, let's take this step function. It's called the floor function because it rounds down. So it's the function that takes a real number, such as 3.5, and rounds it down to the nearest integer, which is 3. So it just does that for all real numbers. What you end up with is this staircase. And let's go ahead and rewrite this function. Now this is one of the huge awesome uses of the Heaviside step functions, is you can take a function like this that's all weird and complicated, and you can write it as a series of Heaviside functions. Now let's think about why this is true. u1 of t, the Heaviside function at 1, turns on at 1. Then u2 of t turns on at 2. Then u3 of t turns on at 3, etc. So when you add all these Heaviside functions together, what you have is precisely this staircase. Moving on. If we want to take the Laplace transform of this function, we can just use the Laplace transform function for the Heaviside functions. The Laplace transform of the Heaviside function is e to the minus ns over s. So there you have it. That's the Laplace transform of our function. which you can then rewrite as a geometric series, and then you get this nice expression that doesn't involve a sum. Although actually this formula here is more useful. We usually like to keep things in series notation when we are dealing with Laplace transforms. You'll see why. So this is actually a little bit less useful. This is what we want right here. But we simplified using the geometric series formula, in case you forgot about this little thing. Alright, so I have a differential equation for you. Y prime of t equals the floor function of t, with the initial condition y of 0 equals 0. So let's take the Laplace transform of both sides. Using the previous problem, we know that the right-hand side is this sum. For the left-hand side, this is the Laplace transform of a derivative. And I actually made a little mistake. That should be a minus sign, but it actually doesn't affect the problem because it so happens that the initial condition was 0 anyway. So whether this is a plus or a minus, thankfully, did not affect this solution. In any case, we have this, y of s equals this. And then if we, so then our goal is to try to find a function whose Laplace transform is this. That's called taking the Laplace transform, the inverse Laplace transform of both sides. So taking a Laplace transform means using the Laplace transform formula, and taking the inverse Laplace transform means asking the reverse question. How do we find a function, lowercase y of t, whose Laplace transform is this? Well, we just do it term by term, recalling some. So I actually haven't really sufficiently explained this, but in fact, hold that thought. I think this problem might actually be a little bit misplaced, because I haven't exactly shown you how to take the inverse Laplace transform of this thing here. So again, maybe hold that thought. But in any case, this is the correct answer, and if you plot it, it looks absolutely perfect. It's the derivative of our function is increasing in steps. It is the staircase function. So it's 0, then suddenly it's 1, then suddenly it's 2, then suddenly it's 3. Interesting point to make here is that at this point, at any of these integers, you can think of this function as having like infinite acceleration, because its velocity jumps from 1 to 2, then it jumps from 2 to 3 in an instant. So in real life, you can't have something's velocity suddenly jump, usually. Although there are situations where it does happen, like if you have a collision. If two objects collide, then their velocities can change discontinuously. So these sorts of things can happen in real life. Yeah, you'll have to excuse the spoilers. I keep screwing up these animations. So let's compute the Laplace transform, the periodic function of period L. Well, if a function has period L, that means it repeats itself every L units. So the only thing you really need to know about this function is its values for t between 0 and L. Then after you know that, it just keeps repeating those values for all of time. So for example, sine of t is a periodic function of period 2 pi. In general, though, we're interested to know how we can find the Laplace transform of a general periodic function, because there are other periodic functions besides the sine function. So what we can do is we can break this integral into infinitely many segments. from 0 to L, from L to 2L, from 2L to 3L, etc. And I've written that as an infinite sum. So that's what I've done is I've taken this interval from 0 to infinity and broken it up into integer multiples of L here. And then if we make a change of variables, letting u equals t minus nl, you get this integral. Let me write. Did I write that down? I guess I did not. So let me write that down for you. If you in order to get from there to there, let u equal t minus nl, and if you do that substitution, you turn this integral into this one. Then you can factor out e to the minus snl, and you're left with this integral, which is the Laplace transform of f bar, where f bar is this function. It's just f of t from 0 to L and 0 for the rest of time. That's just true by definition that this equals this if this is true. And then the geometric series formula allows us to rewrite this as this. However, although the last formula right here is clean looking, this formula is actually better. So again, series are usually a better way to express Laplace transforms. So we'll take this formula to the bank with us as we continue, that the Laplace transform of an L periodic function is what you see here. So let's take the Laplace transform of a square wave function of period 2a. So this is what I'm talking about. It's a square wave. So it's 1, then all of a sudden it's -1, and then it's back to 1 again. And I'm saying its period is 2a, meaning it repeats itself every 2a units. And we're going to find the Laplace transform, so L, the period, equals 2a. So if we want to use this formula, the L periodic formula, then we let L equal 2a because we have a function of period 2a. And we apply this formula, and we just have to compute that integral, the integral from 0 to L of f of t e to the minus st dt. I'll leave this as an exercise, but looking at your function f, it's 1 from 0 to a, and then it's -1 from a to 2a. It's a bit of a lengthy computation, easy enough for the computer to do, however. In any case, you do get this for the integral, which I chose to expand, like so. And then when you put this back into the L periodic formula, we get that the Laplace transform of the square wave function as a function of s is this, e to the minus snl, which is snl, times the integral, which we just found. So this is our Laplace transform. And I went ahead and expanded it. And then actually, these terms here combine with these terms here, not directly, but if you write out this sum, if you write out the first 2 or 3 terms, you'll see that these terms combine with these terms, and you end up with a 2 for those as well, with a lagging term at the end. So if you don't understand how to get from here to here, I would say don't worry about it too much. I'm perfectly happy with you just taking this formula for granted. But it is an interesting exercise to try and expand this sum and rewrite it as this simpler sum here. So we have a formula for the Laplace transform of the unit square wave function of period 2a. a very important formula. Next, suppose we know that the Laplace transform of a function is capital F. Let's find a function whose Laplace transform is capital F of s plus a. So what I'm really asking you here is, can we find the inverse Laplace transform of f of s plus a, given that we know the inverse Laplace transform of capital F is this function. This is our first time really figuring out an inverse Laplace transform formula from scratch. So we're looking for a new function. I'm going to go ahead and call it f bar of t. And we're looking for a function whose Laplace transform is capital F of s plus a. How do we find such a function? Well, let's go ahead and write out the definitions of both sides. And if we do that, we have this integral has to equal this integral. And not only that, but they have to be equal for any value of s. It follows then that the integrands have to be equal to each other for all s. And if we divide both sides by e to the minus st, you end up with this. And that's actually, we're done. This is the function, e to the minus at f of t, whose Laplace transform happens to be capital F of s plus a, as these computations have shown. So we make the following conclusion. The Laplace transform of e to the minus at times f of t is equal to the original Laplace transform of the original function, but shifted to the left a units. Shifted to the left a units. Okay, well, that's a mouthful, but also very useful. And here we go. We're going to take a mass spring system, so it has a mass m, a spring with spring constant k, resistance beta, acted upon by an alternating force modeled by the square wave function with period 2L and semi-amplitude a. We're going to solve the differential equation assuming the mass starts at rest. We're going to assume underdamping for this problem. So we're going to assume beta squared minus 4mk is smaller than 0. And what do we have? Well, this is our differential equation for a mass on a spring. Take the Laplace transform of both sides. And using our Laplace transform formula for the square wave function, this is precisely that formula, written in summation format. Let's solve for capital X. Capital X, of course, being the Laplace transform of lowercase x, and we get this. Now, we make these substitutions for convenience, because with these substitutions, you can rewrite these quadratic expressions in these forms. So it's a little bit simpler to write the sum of two squares formula with these substitutions. Next, we make that substitution, and then we do partial fractions. So we have the fraction 1 over s times s plus gamma squared plus omega squared. When we do partial fractions with respect to the variable s, we end up with what you see here, according to Mathematica. And so we break apart this fraction. Well, first of all, I took the liberty of factoring out a over m over gamma squared plus omega squared, and when I factored that out, this is what we were left with. So I factored this expression. You can stare at that for a while, and perhaps if you're anything like me, it'll take you a few hours to get from here to here. So don't think this is supposed to be an easy simplification process. But do keep in mind this, what you have here in the end is a constant, some function of s and some function of s. So this is our Laplace transform of x. And we're going to use these three formulas to take the inverse Laplace transform and find a function lowercase x of t that satisfies this. So now that we have these formulas, I rewrite the left-hand side, sort of preparing this guy for using the cosine formula together with the shift by gamma formula. So A is gamma. We're taking the cosine transform and shifting it by gamma. That's what we have here. And here I've rewritten it a bit so that it more closely resembles the Laplace transform of a sine. So this is entirely an algebraic simplification to go from here down to here. And now we can take the inverse Laplace transform of this, and I called it g of t. And it's this. And I took this whole constant over here and just decided to call it b. And this whole thing, when you take the inverse Laplace transform, it simplifies down to negative bg of t. That came from this times negative 1 times b. And then the 2 came from here. B came from here. And then for the summation, these e to the minus 2n ls's and e to the minus 2n plus 1 ls's, using this formula, translate to a tau translation of your original function g. So that's what we get here. So this is our function. This is the solution to the differential equation. So let's take mass equal to 2.3, beta equal to 0.4, k equal to 25, amplitude 20, and period or semi-period 3. And I took the liberty of writing our solution just as I wrote it on the previous slide, where I've made the necessary substitutions for our constants. I defined the Heaviside function. You have to use notation if you want to use the subscript, otherwise it won't work. So I had to import the notation package to make that so that I could write it a little bit more cleanly over here. So these are all of our constants, just as I defined them on the previous slide: omega, gamma, b, and then of course the given constants m, beta, k, a, l. And when I take this function, it's actually an infinite sum, but Mathematica isn't so great at plotting infinite sums, so I truncated it, and that's actually going to be a perfectly good answer for a while, up till 60, I believe. And then if you wanted to go past 60, you'd have to add more terms. But there's your plot. So kind of chaotic. Looks like a non-resonant situation. Not even really beats happening here. But let's take a look at constants. This time I have, what have I done? I believe I've decreased the mass. I can't quite remember now what I did, but I definitely increased the amplitude of the forcing function and gave it a much longer period. And the result is pretty dramatic. Basically what happens is the square forcing function just pushes our mass up for a while, but then the resistance, 1.2, causes the mass to slow down and come to a stop. And then it's basically stopped. But then at 12 seconds, because our square wave has a period of 12 seconds, at 12 seconds it jumps down. So it pushes the mass down, it oscillates, kind of freaks out for a bit, but then once again the resistance slows it down to a dead stop, pretty much. And then the square wave jumps back up, and this just keeps happening. So the solution makes perfectly good sense. It's a perfectly good description of what you'd expect to happen if you had a square wave forcing function acting on your mass. So you can take this code. I'll maybe post it online, or you can just copy it yourself, and you can play around with the constants m, beta, k, a, and l, and see what kind of funny little responses you can get to different square waves.